today's podcast, I'd like to continue our conversation about AC circuits. So just to set us into context, on this left side of the screen we have DC circuits. These are time-independent solutions that are always the same, right? We put a voltage on two resistors. We always measure the same potential across those resistors. They don't change with time. Okay, so those values don't change with time. Then we go over there and go, well, that's certainly one possibility. Another possibility is that they change with time. And there's sort of two different ways they could change. On the right, we have transients. Those are values that change, but they die out, right? And so this is when we had resistor, or when we had capacitors and inductors. We saw that the voltage changed and then reached some equilibrium, steady state, DC kind of value. What I want to talk today is continue the conversation about AC circuits, steady state solutions. The solution is the same, but the voltage changes as a function of time. And so what we learned last time talking about complex numbers is that we could describe oscillating functions, and typically we use the sine function or the cosine function, some kind of sinusoidal wave. We can use complex notation to describe that. So I can represent the voltage as a function of time as some maximum, some magnitude, the peak voltage, times something that oscillates. And that oscillating, you can see over here, e to the j omega t plus phi is really just the peak voltage times cosine, or angle, plus j times the sine of the angle. So it's a complex number. There's a real part and there's an imaginary part. We can do the same thing with the current, noticing that the phase constant phi could be different, right? They don't have to be the same. Now we're saying, hey, we can represent this number, right, our voltage and current, as a complex number, but in the end we have to come back and measure it in the lab. And the question is, well, what are we going to measure? We're going to measure the real part, the imaginary part, some put together. Well, it turns out the answer is we're going to measure the real part. So if we go to make a measurement of voltage, we're going to measure the real part of the function of V of t. Or if we go to measure the current, we're going to measure the real part of the current. Okay, so that's just something to remember. We're going to move into this complex notation to make our life easier, but when we come out and we want to know, well, what are we actually going to measure, we have to take the real part. But the phase, that imaginary part, helps keep track of everything that's going on. And then the last thing is power. So power is a little bit more complicated, because when you go to measure the power across some element, say a resistor, and go, well, it's the current times the potential. Well, it turns out it's the real part of the current and the real part of the potential that determine what the power is. Okay. So now, after having spent last week telling you, oh, this is our new non-ohmic device, the inductor, the capacitor, they don't obey Ohm's law. They're a new kind of thing. It turns out, while they're not ohmic, in sort of this AC, if we write them in this complex notation, we can make it like Ohm's law. So we can make it like they're ohmic. And so what do we have to do? Essentially, we just have to define some impedance. And the impedance is given the symbol Z, and it typically depends on the frequency. But here, this is our Ohm's law. The potential across some element is the current through that element times the impedance of that element. And so we can define the impedance as the potential across the element divided by the current. This is exactly Ohm's law, right? But it turns out we're going to be able to do this for inductors and capacitors and resistors, even though inductors and capacitors aren't ohmic. And then we're going to have, our rules are exactly the same. If we could have impedance, right, which could be inductor, capacitor, whatever you want it to be, in series, well, we can replace that with some kind of an equivalent impedance, and how you figure out what that equivalent impedance is exactly the same as for resistors. So if you have impedance in series, you add them, and if you have impedance in parallel, well, you have 1 over the parallel impedance, the equivalent impedance is equal to 1 over Z1 plus 1 over Z2. Okay, so in this sense, everything is the same. So let's take a look at this. What are the actual forms for the impedance of capacitors and resistors? And so just as a starting point, let's go back to Ohm's law, right? We said, hey, for Ohm's law, this is the relationship. The potential across the resistor is the resistance times the current. Well, if we want to find the impedance, or essentially the resistance is just the voltage over the current, right? And in that case, it's R, right? It's independent of frequency. That's just what it is. So we're going to do the same kind of thing with the capacitor and with the inductor. Well, we can write down the governing relationship, the defining relationship for the capacitor. Vc equals 1 over C times the charge on the capacitor. We can do some differentiation with respect to time. We can let the voltage equal to some oscillating function, which we know it's going to be, if that's the kind of signal we're going to put on it. And then what happens when you do that is if you take the voltage of the capacitor with respect to time, or the derivative of the capacitor voltage across the capacitor with respect to time, because it's an exponential, you just get some constant. And so it turns out dV dt is just equal to some constant times the voltage. Or writing it another way, it's like this. The relationship between the current through the capacitor is just J omega C times the voltage across the capacitor. Well, now we have that relationship. We can go say, well, what's the impedance? The impedance is the voltage across the capacitor divided by the current. And we can substitute our value in, and that says the impedance of the capacitor is just 1 over J omega C. Right? It depends on the frequency, depends on the capacitance. Okay, or we could write it in another way that says the impedance of the capacitor is just 1 over J omega C, or 1 over omega C times e to the minus j pi, if we put it in polar form. We can go through and do the same thing, to take the defining relationship of the inductor. We can assume some solution. We can figure out the relationship between the voltage and the current, and then we can find what's the impedance of an inductor, and it turns out it also is equal to a constant J omega L. Okay, where J is our imaginary number, omega is the frequency, the angular frequency, and L is the inductance. And so that's the relationship for the impedance. So if you want to know what's the impedance of an inductor, you have to know what's the frequency of the you're going to oscillate the circuit at, and what's the inductance.